Now we are going to estimate the sum of a series. Well, from the knowledge that we had in the previous videos, now we know that this series converges because this is of the format 1 divided by n to the power p, and here p is greater than 1. So this converges. That means you will have a finite value when you add up all these infinite terms. But the thing is, from those previous tests, it did not tell you a method to find this finite value, right? It's like we know that the total value of this infinite term will be a real number, but we don't know what that number is, right? We only know that this one converges. That means this addition of these infinite terms will give a finite number, but we don't know the value of this finite number. And to compute the exact value of this finite number is nearly impossible, right? It's very difficult to figure out a way to compute the exact value of this finite number. So what we do is we use some techniques of approximation, right? It's like this. So now when we consider this series, you can see that if you add only one term, that is S1, it gives a certain, like if you just consider the first term only, it will have a certain value. And if you take the addition of the first two terms, it is a little bit more closer to this exact answer than the previous one. Now we will denote this exact answer as S, okay? And from the theory that we have learned, we already know that S should be equal to the limit of the sequence of partial sums. And if we know how to write the general term of Sn, then we can easily find out the value of S by computing the limit. But the thing is, we most of the times we won't even be able to calculate or like figure out the general term of this Sn. So it's very difficult to figure out this exact term, right? But just we will denote it by S, right? So what I was telling is that like this S2, that is the addition of first two terms, is a little closer to S than it was for S1. And if we take the addition of first three terms, that is more closer to S than the addition of first two terms. Closer in the sense, the addition of this total three numbers will be closer than, like, it's like let's say that S is equal to 10, right? Just for the explanation, we'll take S is equal to 10. Then the addition of first two terms might be equal to 8, and addition of the first three terms might be equal to 9, right? See, now 9 is much closer to 10 than it is for 8, right? So what happens is, when we include more and more terms in our addition, it will get closer to the exact answer, right? So this is basically the partial sum, right? So now let's say that we have added let's take this one. We have added the first 8 terms. Oh, let's take, anyway, as I have written down 10 terms, let's take it like that. Let's say that we have added the first 10 terms, right? That means now out of these S1 up to S10, S10 is the closest figure to the exact answer. But still it will have a certain error because it is not exactly equal to S. Okay, it is kind of approximately equal, right? So when it is approximately equal, we denote it by this symbol, right? When it is equal, we write two straight lines, but when it is an approximate figure, you write it with some curly lines, right? Okay, right. So now, since this is an approximate figure, that means there will be a difference between the actual answer and with our approximated answer, and that difference can be denoted by S minus Sn, right? So if we have a look at this expansion one more time, now this is the addition of first two terms, which we can denote by S10, right? And how about this, all these remaining infinite terms, right? Here also it has some sort of an impact, right? So if we only consider this thing, like if we consider this Sn only, then it will have a difference between the actual answer and this one, and like the, so you can see that according to this expansion, the difference is the addition of all these infinite terms starting from here, right? So that's basically the value associated with S minus S10, right? So S10 means the addition of all the terms up to the first 10th position, and S means the total answer of all these infinite terms, and S minus S10 will be the value of the value of the addition of all these infinite terms starting from here, right? And we have a special notation for this difference, and we represent it by R, right? R stands for the remainder. These are the remaining terms, right? So here we focus our attention to this number. And another way to look at this number is, it's like, this is like the error of considering this as the answer of our series. That means in our series, that is n to the power 3, from the previous theorems, as we knew that the series converges to a finite value, right? And the exact answer is this one. But if we say that the series is kind of equal to S10, right? That is approximately equal to S10, right? Then there will be an error between this one and the actual answer, right? And that error is denoted by Rn, or we call this as the remainder, right? So simply, if we take the addition of first n terms on a converging series, then Rn represents the error between this approximation and the actual number, right? But the thing is, we cannot find the exact answer for this error, because the thing is, now since these are finite terms, now see, now all like the addition of the first 10 terms is kind of a finite situation, right? We just have to take a calculator and enter all these numbers and we can get the addition. So we can find an exact answer for this one, but the thing is, we cannot, like from a calculator, we cannot find the answer for the addition of infinite terms, right? So we cannot calculate the exact answer for the remainder, right? And on the other hand, if we can calculate the exact answer for this one as well, then the addition of these two will give you the exact answer for the series, right? So that's basically, that's the main point of considering these that's the main problem of these series representations, right? Because we cannot find, from using computers, we cannot find the exact answer for this infinite addition. Hence what we do is we do a approximation, right? So what we do is we take the sum of finite terms, and then as we cannot find the error exactly, we have some tools to determine a inequality for the error, right? Say from a certain method that we have where actually I will mention this inequality now, and then I will go for a problem that will explain everything. Okay, so for the time being, just bear with me, and in the next video everything will be more clear, right? So at the moment what we have in our hand is the addition of first n terms of this converging series. Now from a different method, we should know that this series converges, okay? And we know we have the addition of first n terms, and Rn represents the error. That means the difference between the addition of first n terms and the actual answer of this, right? So Rn is the difference between these two things, right? And this inequality is as follows. Okay, it says, suppose we have a function like this, where this has the same conditions as it was in the previous integral test, okay? And it starts from n, where n is that number that we considered to get the partial sum, right? Then the series is, and if the series like all these are true only when the series is converging, right? And the convergence of the series should be determined by a different test, right? And then the remainder will be in between these two values, right? So let's do an example. We'll consider the same example. If we have the series this one, then we have already shown that this function will satisfy these conditions, right? So it says, now let's say, now even in this explanation I took 10 terms, right? So we are taking the addition of first 10 terms, right? And even if you use a calculator, you can see that the addition of these 10 terms is 1 point, I'll write it here. The addition of the first 10 terms is like this. You should obtain this one from a calculator. It's 1.1975. okay, right? So now we have all the tools. Actually we don't even need this number. What we need is a function and the value of the n that we are going to consider, which is 10 in this case, right? Okay, so then it says that the difference between the actual value and the addition of this, now in this case the value of n is 10, so R10, which is equal to s minus s10, will lie between these two integrals. So what you will have is n plus 1, and that is equal to 11 infinity fx dx, and Rn will be R10, and here you will have 10 up to infinity. Okay, now there are some things that I want to highlight here. Okay, this R10 value is a term that is obtained from the series, right? This starts from 1, and this R10 goes like it is obtained from calculating certain things associated with the series. But the thing is, in this inequality, on both sides you have an integral, and the integral will goes with this function, right? So that's the relationship. Okay, that's the reason why we need a function, right? And here also we are not discussing any proofs, right? I did not mention why this inequality holds true, right? We just take it for granted because the proof of these inequalities are very very complicated, right? So we just take this as we just directly use these theorems without any proofs, right? So, and the special thing here is that the center value goes with the series and the two outside values goes with the function, right? So that's how we relate everything to each other, right? Okay, and then by computing this improper integral, you can see that like if we compute it in general for a general k, this integral will be equal to 1 over 2n squared. You just have to do it through a limit. Okay, and so since no, I'm sorry, this should be 1 over 2k squared. Okay, right. So accordingly, now that means whatever the number we use as the lower limit, it will come like this, right? The answer for the integral. So accordingly, the answer for this integral will be equal to 1 over 200, right? And this one will be equal to 1 over 242. Okay, because here k is equal to 11 and that is 2 times 11 square. Okay, so from this inequality we can say that the remainder is in between 1 over 200 and 1 over 242. And if we just find out some like if we represent these terms in a decimal format, it will be a value like this. Okay, so that means when you add the first 10 terms in this series, right, when you add the first 10 terms of this series, and when you consider the remainder or the error, right? So this is the remainder from that comes from the addition of first 10 terms, right? Then this one, now I said the answer for the addition of first 10 terms, which can be computed by a calculator, is equal to 1.1975, right? So that means the actual value of this series and the addition of first 10 terms, which is equal to this one, will have a difference no more than 0.005, right? So it's like if we write the series to be equal to this number, which is 1.1975, then definitely there will be an error, right? This is actually not equal because this and this are not equal. But the thing is, this difference, this error will not be greater than 0.005, right? That's the importance of this inequality. Although we don't know the exact value of this error that is caused by taking only the first 10 terms, we know for sure that this error will be not greater than 0.005, right? So in other words, we know for sure that the actual answer for this value, for this series, will not be a number like this, right? Like the actual answer for this series will definitely not be equal to 10, because if this is the actual answer, then the actual answer minus S10 will be something like 8 point something, which is way more greater than the predicted error, right? So like this inequality is a very powerful tool, okay? Although we cannot find the actual answer, we can find a specific region for this answer to occur, right? So if this is 1.1975, then the actual answer should lie should be within at a maximum distance of 0.005, right? That can be concluded from this side of the inequality, and from this side also you can mention something. Now here you have the addition of first 10 terms, right? And the actual answer should lie between these two, and in this left hand side of the inequality says that the error must be greater than 0.004, right? So that means the actual answer cannot get too close to this S10 value, right? So it's like it cannot be very close to this S10 because it must have an error greater than 0.004. So that means you must leave a gap of about 0.004. Now my diagrams are not according to a scale, right? So anyway, you must leave a gap of 0.004 to this S10 value. Now this is the S10 value, so the actual answer must lie within one out of these two regions, right? So now we know for sure that the actual answer will lie one out of these two regions, right? So that's the importance of this inequality of the remainder, right? So if we summarize what we have done so far, now initially we had a series, right? And it was 1 divided by n cube, okay? And from a different test, that is basically the p-test, we said that the series converges. So that means the series should have a finite value, but we don't have sufficient tools to find the finite value, right? So what we do is we just added the first 10 terms, but since we have only added the first 10 terms, we know for sure that it will definitely have an error with the actual answer, which is S, right? And from the inequality, that is the new theorem that we learned here, from this inequality, it says that although we don't know the exact answer, we have necessary tools to determine a inequality for the error, which is in this case 0.05 and 0.04, right? So from this one, we were able to figure out a region where the actual answer might lie, right? So it should be one out of these two regions that the actual answer should be, okay? Right. And in the next video also I will continue with this problem and some more insight.